Hey everybody, welcome back to linear algebra. Today we're talking about linear independence, and I'm just going to warn you, linear independence has a reputation for being difficult to understand the first time around. So if you're not getting it, don't feel bad. There's not something wrong with you. You need to get it, obviously. So keep trying. Talk to me about it, and we will get you there. But the big idea for today is we want to know what it means when the homogeneous system of equations ax equals 0 only has the trivial solution. Now I know I told you we weren't very interested in the trivial solution. I said the trivial solution was boring, but it does come with some interesting properties. So what we're going to start with is the definition for linearly independent. Let's say we've got a set of vectors v1 to vp. We call them linearly independent if we can write x1 times v1 plus x2 times v2 all the way up to xp plus times vp is equal to 0 is only possible for the trivial solution, aka all your x's are 0. The only way to get that sum equal to 0 is when the coefficients themselves are 0. Otherwise, the set of vectors is said to be linearly dependent. So what we get from this otherwise is what it means if there exists some x that is not equal to 0 and this guy, I can write this, still holds, that's when we get linearly dependent, is if we have non-zero coefficients but it's still equal to 0. So how does this relate to ax equals 0? Well, I'm going to say, suppose a was equal to v1 up to vp. So the vectors were the columns of a. Then we would have a times x equals 0 is equivalent to that sum right there. So in fact, our very first lemma is about the ax equals 0. So the vectors v1 through vp are linearly independent if and only if ax equals 0 has the trivial solution for a equal to all those v's as columns. Okay. So now remember the definition said otherwise we call it linearly dependent. What does otherwise mean for ax equals 0? Remember we have three possibilities for ax equals 0. No solution, unique solution, infinitely many solution. For no solution, we know that that's not possible. We were always guaranteed the trivial solution, so it's not that. The trivial solution was the unique solution, and so trivial solution equals independent. So that means for dependence, we need a non-trivial solution. That's the only option left. So we've got linearly dependent if and only if ax equals 0 has a non-trivial solution. And we're going to illustrate this in an example right here. So we're going to check if these three vectors are linearly independent or dependent, and we can do that because we know things about solving ax equals 0. All we need is an augmented matrix. So here we go. Here is our augmented matrix. And what I'm going to do is I'm going to put it into row echelon form. I'm going to start by knocking out that 2. So R2 minus 2R1. Row 1 does not change. We copy him down. And then row 2 changes. And we get -3, -3. And then I'm going to be bad and lazy. And I'm going to take out this 3 in the same step. There we go. So you can probably already see row 3 is going to get killed off by row 2. Okay, and then row 3 changes, so now we write him. There we go. So, what does this mean? We have hit row echelon form. We have a free variable. What does having a free variable mean? It means non-trivial solution. What does a non-trivial solution mean? Well, just have it up above. It means linearly dependent. And to prove that it's linearly independent, we can go through and check real quick. So the check is, can we find coefficients that are not 0 and still get 0 on the right-hand side? I'm going to do that by going to reduced row echelon form. 1, 4, 2, 0, 0, 1, 1, 0, row of zeros. And we can knock out this 4 that we have right here. We can do row 1 minus 4, row 2. Let's see, row 3 stays the same, row 2 stays the same. And then row 1 changes. And we get 0, negative 2. Okay, so now that we have that, that means we have this system of equations. We're going to solve for x1 and x2. And I'm going to give myself some more space real quick. Here we go. So x1 equals 2x3, x2 equals negative x3, and then x3 is free. There we go. So yes, if x3 is 0, you get x2 is 0 and x1 is 0, but linearly independent means only has the trivial solution. So all we have to do is find other solutions. So if we let x3 equal 1, we're going to get an interesting solution. So then we end up with 2 times 1, 2, 3 minus 4, 5, 6 plus 2, 1, 0 equals 0. And if we substitute that back in. So indeed, we have found non-zero coefficients. And we've still got 0 on the right-hand side. So that means the trivial solution was not the only solution, therefore linearly dependent, just as we said. Okay, so implications of linear dependence. So this is for those of you that said maybe it looked like a linear combination. Yes, it did. You get from linear dependence, that means you end up with these non-zero coefficients over here. You can write one vector just by rearranging things. You can write one vector in terms of the others. It is a linear combination of the others. You might even say it depends on the other vectors, hence linear dependence. For instance, we're going to recall real quick from our very recent slide. We had this guy. And I'm going to move vector 2 to the other side. There we go. So V2 is now a linear combination of V1 and V3. Okay, because we've got a linear combination, it's scalar times vector on the left-hand side. So that brings us to our first theorem of today. This is theorem 7 in your book. If it's a set of 2 or more vectors, V1 to Vp is linearly dependent if and only if you can write one of those vectors as a linear combination of the other ones. Warning, this does not mean every vector can be written as a linear combination of the others when you have linear dependence. You just have to have one that you can do this for. And I will have an example coming up soon where I can illustrate this. So we're going to start talking about some special cases. Suppose that we have only one vector. Is this linearly independent or dependent? Well, linear dependence implies C1 times V equals 0, and C1 is not 0. So then the only way to get it equal to 0 is if V is equal to 0. So then if V is not 0, so if V is not 0, we have linear independence. It's not entirely interesting, but it is true. Now let's get a little bit more interesting. Suppose now we have 2 vectors and they're linearly dependent. What can we get? Well, that means we have C times U plus C2 times V is going to be equal to 0, and at least C1 or C2 is not 0. I'm just going to pick one. We're going to say assume it's C1 that isn't 0. And you could pick C2, it doesn't really matter. These are arbitrary. C1 is pretty much as good as C2 because U and V haven't been defined. Okay. So if we assume C1 isn't 0, then we can say that U would be equal to negative C2V over, I do not like that. There it goes. Over C1, and we're allowed to divide by C1 because I said C1 wasn't 0. That's the important part of saying C1 wasn't 0. So then, since C2 is a constant, C1 is a constant, you can just say U is equal to some constant times V. AKA, U and V are going to be linearly dependent if one of them is a multiple of the other one. All right, our next special case that we're going to think about is, let's say we've got multiple vectors and one of them is 0. What do we say about the linear independence for that? So I'm going to say, well, let's do 1 times 0, and then I'm going to make 0 the coefficient for everybody else. So since the coefficients are 0, all those terms are 0. And then the 0 vector times any constant is going to be 0. So you have 0 plus 0, and that's equal to 0. Therefore, I found something where a coefficient was not 0, so non-zero, which means that we have linear dependence again. Okay. So that means whenever you have 0 in your set of vectors, you're always going to have linear dependence. This illustrates my warning that I told you I was going to have an example for. I can say that 0 is a linear combination of these guys by putting them over on the other side. I cannot say anything about like VP. VP, if I put him on the other side, then all I've got is 0 on the other side still. Can't say anything about him. Okay. Last special case. What if we have more vectors than we have entries in those vectors? So like we have 4 vectors, but we only have 3 entries in each vector. That brings us to a theorem. If we have p many vectors in Rn, which means we have n entries, and p is bigger than n, so we have more vectors than we do entries, then the collection is linearly dependent. This is Theorem 8 in your book. And the reason for this is we're going to say A is going to be the vectors as columns. Then we have A has the form like this. P many columns and only n many rows. After Gaussian elimination, A will have at most n pivot points. Has at most n pivot points. This may sound a little bit familiar from your first worksheet. I asked you about the solutions to a 4x6 augmented matrix, and you had to give me some information. That was question 2. Same idea. A has at most n pivot points because it only has n rows. That means we have at least p minus n, and this is greater than 0, free variables. And this is greater than 0 because I said p, highlight. P is greater than n, so then p minus n is bigger than 0. So if we have free variables, then we have a non-trivial solution, and that means we have linear dependence. All right, so now that we have some special cases, let's look at an example with some special cases. Here we go. We have 4 by 3. So we have linear dependence because we have more vectors than we do entries. For B, we can say that 2, 0, 0 is equal to 2 times 1, 0, 0. And so we can say this guy is linearly dependent. That was that special case right there. And then we've got our final one, and you can see just by looking at it, if we write it out like this, the only way to get it equal to 0 is to have C1 and C2 both be 0 themselves, because this top row right here, this guy and this guy, the only thing that's going to affect them is this entry of 1 here. And so we can only get 0 in the top row if C1 is 0. And then same thing goes for row 2. You can only get 0 in the second row, if this plus this is 0, which is only going to happen if C2 times 1 is 0. So C2 is 0. So without even having to solve for it, I can say that it's linearly independent. Okay, so that brings us to our last section, geometry and linear independence. Remember that linear independence, or remember that span has like geometric interpretations, which is why theorem 3 is sitting here. We say that a set of vectors is linearly independent if at least one of those vectors is in the span of the others. And the idea behind that being is we've got V1 to VP are linearly dependent. Linearly dependent means that we have linear combinations, which means that we have span. So for example, we're going to bring back this lovely problem, example 1. Remember I said we had 2, 1, 2, 3, minus 4, 5, 6, and plus 2, 1, 0 was equal to 0. And then I moved vector 2 to the other side. So then we have this is equal to vector 2, which means that we can say 4, 5, 6 is in the span of the other two, because we found a linear combination. This is the advantage of not working on a whiteboard, is I can just move things. It's wonderful. There we go. So we talked about linear independence today. We discovered that it was really just the same thing as looking at homogeneous systems, which is still the same thing as linear combinations and span, just like it has been for the past couple of lectures. Again, if this is not sitting right with your brain, I'm gonna flip back. Oh no, come into focus. Well, anyway, this lemma right here, understand this lemma. If this is what you walk away with, is that was the only thing that you understood, then I'm going to count it as a victory. I don't know. My computer's spazzing out, so it must be time to say goodbye. I'll talk to you guys another time.